Hi, this is lecture 18 of engineering physics. In this lecture, we will continue studying rotations, and we will start by combining rotations with translations. So if you remember in the very beginning, when we started with the motion, we would only consider translational motion. We had objects, and those objects would move around in many different ways. But we usually ignored the fact that this object had some structure and it may have been rotating or otherwise changing its orientation in space. And last week, we did the opposite. We looked at extended objects. Those objects were somehow fixed. They had a pivot point, and they would rotate around that pivot point, that they wouldn't otherwise move. Now, in real life, when objects move, usually, more often than not, they will do both translational motion and rotational motion. A good example of this is, of course, a simple wheel. For example, it would be a bicycle wheel or a car wheel. So we have this circular wheel, and if there is no slipping here, then as this wheel moves to the right, like so, it will also be rotating clockwise, like so. And if you think about this, it's kind of obvious that the translational motion of this wheel is related to the rotational motion of the wheel. If the wheel moves faster and there is no slipping, then it will also rotate faster around its axis and the other way around. If you remember what we talked about last week about circular motion and how the point on the rim moves, then you will realize that the relationship between translational speed and rotational speed of this wheel is very simple. And this relationship is that the speed of translational motion is equal to the speed of rotational motion times the radius of the wheel. So there is this very simple formula. Every time you have wheels rolling or any other round objects rolling, this formula relates their translational velocity to their angular velocity. But you should remember that this is only true if there is no slipping. Now, if there is slipping, you can think about your car wheel stuck in mud. Then if there is slipping, then this wheel will rotate faster than it moves forward. And in the extreme case, when it's completely stuck, it will just rotate and it's not going to move forward. And the second extreme is when this wheel moves faster than it rotates. So if it moves very fast, but it doesn't rotate very much, then, again, here you will have, instead of slipping, you will have some sort of sliding. As this wheel moves, it will be, these two surfaces will be sliding against each other. So this is, this was on slide 2, and this is the key formula to remember. Now, if we move to slide 3, slide 3 shows a few examples of rotational plus translational motion. We have this bicycle wheel. We have a spherical object on a ramp, and it rolls down. And then we have a bowling ball that slides along the floor. And it's one thing that I want to kind of highlight is that it's not always easy to figure out what exactly friction is doing when we have rolling. There is always friction involved in one way or another, but what exactly is the direction of friction is not always obvious, and you should always kind of pause and think about it before you proceed solving the problems. So let's start with this bicycle wheel. If the bicycle is moving, then it's moving because you have something here, and the something is applying torque. And the torque makes bicycle wheel rotate. And to figure out what the friction is doing, it's usually a good idea to imagine what would happen if there was no friction. So if we imagine that there is no friction between the bicycle wheel and the surface, then this bicycle wheel would just be rotating and it wouldn't be moving forward. But because there is a friction here, this friction prevents bicycle wheel from moving this way. Now this is the slipping motion that it prevents. And because of this, the friction in this case is actually pointing forward. So in this case, the friction is actually pointing forward, and it's actually the force of friction that makes the bicycle move. If there was no friction, there would be only rotation, there would be no translation. Now, if you think about the second case where you have this sphere and the sphere is rolling down inclined plane, then the situation is slightly different. Again, if you think about the forces that are involved, you have this force of gravity, and then you have this normal force, and then there is friction. So the question is now, which way is the friction pointing? To figure out which way the friction is pointing in this case, again, we want to imagine what would happen if there was no friction. And if there was no friction, what would happen would be that the sphere would simply slide down without rotating. So if there is no friction, then there is really no difference between the sphere and the box. And since now, if we switch the friction back, then what friction does is it tries to prevent the surface of the sphere sliding like this across the inclined plane. So in this case, friction is actually pointing backwards. In this case, friction is pointing backwards. It prevents sliding of the sphere. And if you are sitting, if you imagine sitting here at the center of the wheel, then from your point of view, it's the force of friction that causes this rotational motion. It's the force of friction that provides torque. Now, if you think about the bowling ball, I don't myself bowl very often, so I don't have a lot of experience with this. But bowling ball is a heavy sphere, and if you slide this bowling ball, so when you slide it, it rotates and it moves forward. And when you slide it, it's unless you're really precise, this relationship between angular velocity and linear velocity is not necessarily going to be satisfied. And so if you slide it very fast, if this velocity is high, then this bowling ball is not gonna roll, it's gonna slide. So it will be rotating, but it will be sliding. The force of friction will be applied here. This force of friction will try to prevent sliding. It will be slowing down the bowling ball. And at some point, when the bowling ball's velocity slows down enough so that this relationship is satisfied, the bowling ball will start rolling without slipping. So this is basically what I wanted you to keep in mind. You will have a bunch of homework problems where things roll. And when the things roll, one thing that you know is that how fast they rotate and how fast they translate in space isn't completely independent. This relationship has to hold. So next thing that I want to talk about is rotational energy. We very briefly touched on this last week. And the basic idea here is that if you have something that rotates, let's say you have the sphere, and it rotates around axis, it takes some effort to make objects rotate. And if they are rotating, it takes some effort, some work to stop them from rotating. And that tells you that there is actually energy in rotation. So to make things rotate, you have to do some work. We also had formula for rotational energy. I will write RE here and on my slides. This is now slide number 4. And the rotational energy is given by the formula I omega squared divided by 2, where I is moment of inertia and omega is angular velocity. So this expression is kind of similar to the expression that we had for translational motion. When things were just moving, we had this expression for kinetic energy, and kinetic energy was equal to mass times velocity squared divided by 2. Now, what does this mean? This means that if you have something that's rolling, let's say you have the sphere and the sphere is rolling and moving, you have to keep in mind that this sphere now has 2 types of energy. There is some energy in its motion, linear motion, and there is some energy in its rotation. So to understand better why this is relevant to physics, let's look at some specific problems, at some specific examples. One example that I want to look at is the simple example that we had before of a sphere rolling down a ramp. So let's say I have a sphere that starts from here. You know, this could be 2 meters. And then if it's initially stationary, it will start rolling down. It will start rolling down, and by the time it reaches the end of the ramp, it would have gained some velocity. So it will have some linear velocity, and it will also have some angular velocity because the sphere will rotate as it rolls down. So now let's say we know the mass of the sphere, and we know its size, its radius. The question is, what's its velocity by the time it rolls down? Now, usually, if this was a box and there was no rolling and no rotating, what we would do is we would write down the conservation of energy. We would say energy in the beginning is equal to energy towards the end. And then energy in the beginning would be mgh. And energy towards the end would be mv squared over 2. Now, this line doesn't change. Energy is still conserved. But this line, we will have to change slightly. We will have to change it because we have a sphere. The sphere rolls. So it has this kinetic energy, and plus it has energy of rotation, and the energy of rotation is I omega squared over 2. Okay, so let's look at this equation. Now, mv squared over 2, the meaning of this term is clear. Let's think about this term. So let's start with the moment of inertia. Moment of inertia tells us how difficult it is to rotate things. And we have a sphere here. So for a sphere, I will just look into the list in the textbook, and the textbook tells me that if I have a sphere, then my moment of inertia is 2/5 of mass times radius squared. So the moment of inertia is 2/5 of mass times radius squared. I will use this expression here in my conservation of energy, and I will get 2/5/2 mass times r squared times omega squared. So I will cancel out these two. Now, there is one more thing that I can do here, and this one more thing is that I have radius times angular velocity. And if you remember from a few slides back, if I have rolling without slipping, then the velocity, translational velocity, is radius of the thing that's rotating times its angular velocity. So what I can do is I can replace this r squared omega squared by v squared in here. And if I do that, I will have mgh is equal to m/2 v squared plus 1/5 mass times v squared. And from here, I can cancel out the mass, and I can find my velocity. My velocity will be the square root of gh divided by 1/2 plus 1/5. So let's look at this equation, and let's think about how this is different from just a box sliding down the ramp. This is different because you have this extra term here that takes away some energy. And if there was no rolling, then we wouldn't have this term, and we wouldn't have this 1/5 here. We would be dividing by a smaller number, so our velocity would be higher. And this formula actually shows that because there is rolling that takes away some energy, the velocity at the end is lower than it would be because some amount of energy was spent into making the sphere spin. This all makes sense so far. Now, next question is, what if I had, instead of the sphere, what if I had, for example, a hollow sphere? And the hollow sphere is shaped like a sphere. The only difference is that, and it has the same mass, it's just this mass is, at the edges of the sphere. It's a shell. And if you remember how the moment of inertia works, the way it works is that the further away the mass is from your axis of rotation, the more difficult it is to spin things. So the moment of inertia for a hollow sphere is, instead of 2/5 of mr squared, it's 2/3 of mr squared. So the moment of inertia of a hollow sphere is higher than the moment of inertia of a regular sphere, given the same mass. And what we would do if we had a hollow sphere is we would do exactly the same thing, except in this formula, we would have square root of gh 1/2 plus 2/3. Sorry, 1/3. And so what's happening here is that since the moment of inertia of a hollow sphere is higher, you are dividing by a larger number, your velocity would be even lower. If we were rolling a hollow sphere, our velocity at the end would be even lower. And that's because hollow sphere is really, really difficult to rotate, and it takes much, much more energy, and therefore there is less energy left for the linear motion and kinetic energy associated with it. You can try other shapes. For example, you could try, instead of a solid sphere and a hollow sphere, you could try a cylinder or something else and see how it works out. The general rule is that the harder things are to rotate, the higher their moment of inertia is, the more energy they take away. So the objects are usually slower, all other things being equal. So this is the end of part 1. In part 2, what we will do is we will look at more problems that involve conservation of energy, and we will see how rotations affect these problems.